So, now what we have got is this is the final cleaned up form that you get, that is the in terms of the total this is what we have essentially done. We had from the this is the from the internal energy equation. Okay, we have obtained this equation for total enthalpy, and then we have obtained in terms of this species in terms of the sensible enthalpy. How? We just took this total enthalpy equation, and then we took the equation for the species mass fraction. We multiplied the species mass fraction equation with the corresponding enthalpy of formation for the ith species, and then we subtracted that and we summed over I is equal to 1 to n, and then we subtracted that equation from this equation. Okay, and then we are left with essentially is the equation for the sensible enthalpy. All right. So, this is once again we have, as we have seen, that this is the transient term and this is the convection term, and this is the term that we get because of different heat capacities, and that because species of different heat capacities are crossing the boundary or crossing the control surface or the element surface, infinitesimal control volume surface through you with this species diffusion velocity. And of course, energy is crossing the control surface through lambda grad T, and then there is a pressure dP dt term, and this is the very important heat release rate term, which we denote by HRR. All right. So, this is the equation that we have got, and then of course, you can ask that why have we used the dP dt? Because of the isobaric assumption, our pressure does not depend on spatial locations, it does not depends on in space, it does not change in space, we assume it is constant, and hence dou P dou T is essentially dP dt is P is only a function of temperature. All right, and from that, as you know that because H I S T with respect to T0 is nothing but integral T0 to Tcp I dt. Because of this equation, because of the dH dt is essentially Cpi, that is the definition of Cpi, we can convert this equation into a equation of temperature. All right, and that is a very common form. This is how you actually solve the energy equation in a CFD code or or when you are analytically computing some flames. And this is an example of simplification. It involves some more simplifications though, with some assumptions as will come later. So, but this is the equation, that is rho Cp. There is a total derivative of temperature is essentially this diffusion term. This is the heat conduction term minus the plus of course this one, that is which arises due to the different Cpi's, and then the heat release rate term. All right. Now, then the equation is, this equation is valid under of course the following assumptions you must remember, but this is the equation that you have to solve in addition to other equations. If you have to if you are solving for combustion in a CFD code or for analytical calculations, as I said, but this equation is valid only under this following conditions, and these are that we do not use any body force term. We do not have any body force term, and the diffusion velocity is approximated using a mixture average formulation. I will come to that later. That is and then we have that is here it is similar to this DIN essentially, but we assume that it's the diffusing species is diffusing in a bulk average mixture rather than in a particular species, and then we have neglected the effect of pressure gradient, and second order diffusion in terms of Soret and Dufour is neglected, and there is no radiation. So, these are the restrictive assumptions. If these assumptions are suitable for your condition, you can use this equation in a CFD calculation or analytical calculation. So, now we need to basically see now as we have seen that this is the species concentration, and this is of course the species equation, then that this is the transient term once again, and this is the convection term, and this term arises once again because of the species can cross the control surface with different species diffusion velocities, and of course this is the species production rate term in terms of in units of mass, right, and we have of course used this is this we have assumed that Vi is essentially proportional to gradient of the species mass fraction. Now we can simplify this, as you see that this all the Cpij or Dij, these are difficult to handle. So we will consider two limits. The first limit is that we will consider that the Cpi's, that the specific hits is species specific, but our Dij is equal to constant, is equal to D. Alright. So then we can see that this, we can write this gradient of enthalpy in this form, and we will see that we can write this guy this summation of I is equal to 1 to n yi times gradient of his in essentially as Cp times gradient of T. And anyways, the final equation that we get, you can already also do this derivation, and what we will finally get is that under this restriction that our Cpi is distinct but our diffusivities are constant, which is equal to D. We will get this equation. This is essentially density, and we will see that this is the equation that is get is d rho dhs dt is plus, this is the thing, divergence of rho v hs minus rho d gradient of hs. Here we see a Lewis number coming. Lewis number is nothing but thermal diffusivity by the species diffusivity. Okay. So this is the thing that we get. Now here we get a Lewis number dependent, and then of course of the pressure gradient, pressure derivative dp dt minus the heat release rate term. And this is the species conservation that you get. Of course, the point to note here is that, and both to note here is that this our D is essentially constant, which is an artifact of the fact that we have assumed distinct we have assumed distinct specific hits but constant diffusivities, and D similar diffusivities, that is Dij is equal to D. Okay. So now interesting point to note is that this Lewis number comes up in the energy equation, and which clearly tells that if the Lewis number is not equal to 1, that if this say for example the Lewis number is greater than 1, this will this term will be negative and it will essentially act in some other way, whereas Lewis number, if it is less than 1, then this term will be positive and it will act in a different way. Okay. So then the Lewis number is essentially can act as a source or sink in this energy equation, this Lewis number dependent times gradient of T. Alright. So this is an interesting observation, that the Lewis number first shows up in actual governing equations when you do the distinct specific heat formulation. So, but if you do the distinct diffusivity formulation, that is you assume that the specific heats are essentially same and Dij is equal to Din, and then you get you do not have that term, because now your constant specific heat, as we discussed, that this second term, the summation yi hi vi, capital Vi, that term drops out, and you get a simplified energy conservation equation, which is nothing but this d rho dt d rho hs dt plus this convection of enthalpy. So the enthalpy can be changed by when rho hs, that is the enthalpy itself, is a function of time, and then you have this enthalpy is convected, and then you have heat conduction coming from a temperature gradient, and then you have a pressure derivative, and then you have heat release. Once again, this is the heat release rate term. All right. And then you have of course the species conservation. So now you see that this is actually a very useful form which often people use, because they assume constant specific heats and diffusivities are different. And here the species conservation, you see once again that this is the transient term, and then this is the convection term, this is the species diffusion term, and this is the species production or consumption rate, Wi, depending on the sign. Okay. So basically you see the chemistry comes into here and into here, and through so what happens is that you see that these two, another interesting thing to note is that this energy equation and the species equation at this form, it is interesting to note that these two are coupled, right. How is it coupled? Can you see? It is not apparent, because this essentially Hs is, we can write it in terms of temperature also. It is coupled actually through this. Okay. So through these things. So this omega I, if you remember this as a form of like k times production rate of Cj nu j dashed. Okay, j is equal to 1 to j is equal to 1 to n. All right, and of course this also comes here. And okay, let's write it down, right. So to see basically how this coupling happens. So what I say is that it's this coupling between these two things happen through here. Okay, and the coupling happens because omega I is nothing but nu I double dashed minus nu I dashed. If you assume a one step reaction, that omega I is essentially contributed from one reaction itself. Of course, it is coming from all reactions, and you have to sum over all k, but I will not go to that right now. And then you have the k term, that is this k is a reaction rate constant times the continued product j is equal to 1 to n Cj times nu j dashed, and then k is nothing but b times t to the power of alpha exponential of minus Ea by r 0 t, right. So, you see that this in the species equation, when you write this, this is the omega I form, and then this k contains this temperature dependence. So, actually even though it is not apparent here where temperature arises, of course the temperature comes through here, right. So, the reaction rate contains a constant, the reaction rate constant contains temperature. So, that affects changes in the species mass fraction, and that of course you see that of course temperature changes density also, right, and then this also changes here, okay. And you see that Cj is essentially is a species concentration, and we can write this Cj as essentially in terms of mass fraction. So, this energy conservation, the specific, the sensible enthalpy actually couples with the species equation through this law of mass action term, right. So, this is how the coupling happens, and furthermore when temperature changes, the density also changes, and then you have to consider the continuity equation, and then all these things. Of course, the flow also accelerates when the density changes, because of the simple thing that your continuity equation is nothing but d rho dt plus divergence of rho u vector is equal to 0. So, when the flow accelerates, so when the density changes, the flow also accelerates, and of course your momentum also changes because the rho u is equal to fixed, but then the flow also accelerates, and that is happened due to associated with a small change in pressure, but of course we have neglected the pressure here. But here this gives you an idea of how the coupling is happening. It is very important at this stage to understand that this how the coupling actually takes place through these different sets of equations, because there are plenty of equations involved, but it is very important to understand what each term represents and how each equation is coupled to the other equation, because if it was not coupled, then life would have been much simpler. We would have solved this separately, but that we cannot do that. If you are solving, if you are doing a CFD calculation of a combustor, of a gas turbine engine, you need to solve all of these equations together, okay. And of course you note that this is for ith species. So, if you have a if you have 1,000 species, then there will be 1,000 species conservation equations, okay, and this will run from I is equal to n2, that is I, the summations will run then from I is equal to 1 to 1000 hi naught omega I naught. So, this all the species, the entire chemistry reaction mechanisms that you see gets concentrated into this term and this term, okay, where you need to sum over all the species to get the heat release rate, contribution from all the species to get the heat release rate, and you need to have the species equation for all the species, that is then you will end up with 1000 equations. So, if you have 1000 species, of course due to mass conservation, because of the fact that summation yi will be equal to 1, you need to solve for one less equation, but the total number of equations then you will have is that is essentially you see you will have to solve one continuity equation, 3 momentum equation, 3 because velocity is a vector, momentum is essentially a vector, 1 energy equation, but that energy equation will contain contribution from all these species I is equal to 1 to n, and then n minus 1 species equations depending on the number of species you have, okay. And then of course then you see that it is 2 plus 3 5 plus n minus 1, that is equal to n plus 4. So, typically for a large hydrocarbon like kerosene, if you have like say 1000 species, then it will be 1004 equations, partial 1004 partial differential equations that you need to solve. Now, this looks very challenging. Of course, it is challenging, but then this is why it is so exciting and it is so complex, okay, and but we need to understand it at a very detailed level, because combustion, as you see, is very important if you have to improve modern engines, if you have to design new engines, if you have to make current engines more efficient in terms of producing more power, more thrust, and have greater efficiency. So that is why it is very important to understand them. Now, so the characteristics of the simplified conservation equation is that we have retained the unsteadiness, we have retained the diffusion. By diffusion we mean both species diffusion as well as thermal diffusion, that is heat conduction, and we have retained convection, which is a first order quantity, and of course we have retained reaction rate, because combustion is represented by the reactions, right, and of course it is also contains diffusion and reaction. Now, density, as we have seen that rho v and d appear together with rho and rho v as rho d, and also applies through the Lewis number. But as such, as you see that in a combustion, the density is a very important. We cannot absolutely assume density is constant. That is one very big difference. That is, these are not as such compressible flows, in the sense that these are not high Mach number flows. That combustion can happen in low Mach number. Example, in a gas turbine engine, combustion happens in a Mach number of about 0.1, right, 0.1, 0.2, like something like that. And the pressure inside a gas turbine engine, of course, it's a combustor is at a very high pressure, 30 bar, but the pressure does not change at all in a gas turbine engine. Pressure change is very small in compared to how it changes through the compressor, how it changes through the turbine, right. So pressure change is very small inside the combustor, but temperature changes by a huge amount, and because temperature changes, the density changes. So we can assume it's like an isobaric flow. Of course, it is not actually isobaric. When you solve for the momentum equation, you need to retain your pressure. If you are doing a CFD calculation, you need to retain your pressure terms. But it is close to an isobaric flow, but it's strongly temperature varying flow. There is strong non-homogeneities in terms of temperature. Temperature rises as soon as you have the flame, and of course you have density changes. So as soon as the temperature rises, the density also drops. Okay, because pressure is constant, so P is equal to rho RT. If pressure is constant, so density has to drop when temperature rises, right. So these combustion flows are characterized by small change in pressure, very large change in temperature, and very large change in density. Okay, so these are the hallmarks of combustion. Alright, and then we will see later that also this change of density and change of pressure, change of temperature, no change of pressure, change of temperature happens in a very small regions in space, and as such that is an artifact of the that arises because your activation energy is a very large quantity, and that when you are, because of the nature of the reaction rate constant, it's essentially K is e to the power minus A by RT. So when the activation energy is very large, your temperature rises in a very thin region, and that is why the flames are thin, and that is why you have got very strong temperature gradients. That is, temperature rises in a very small amount of time. So that is why temperature gradients are large, and when temperature gradients are large in diffusion, because you see diffusion is essentially comes as like a grad of rho lambda grad T. So it's essentially del square T, right. So it's essentially a Laplacian of temperature, or is a Laplacian of species mass fraction. So when the gradients are very large, this del square, the second derivatives are also typically large in these regions, and that's why diffusion becomes a very important phenomena. So combustion is essentially, as you will see later, within the flame, combustion is essentially a competition between diffusion, or not a competition, it's essentially a balance between diffusion and reactions, right. So and then that happens can happen in a flow that is convecting also, but we will come to these things later. So the of course important thing is that the sign of the diffusion term is negative, and that arises because temperature changes, heat flux changes from when you go from heat always flows from a temperature of high temperature to a low temperature region. Alright, so now the thing is that the chemical source term, as you see that we can write it now as like in terms of species mass fraction. If you have of course there will be some constants in terms of molecular weights, etc. Then we can write the omega I, that is the reaction rate constant, is essentially yi nj times yj nj e to the power of minus e by r0 t. It's nonlinear in both y and t. Okay. It is nonlinear in Y because it has got exponents which are the stoichiometric coefficients, and it is nonlinear in T because of the e to the power of minus A by R 0 T, and it couples the conservation equations for Y, I and T. So, now, so this is a problematic thing because it appears in both species equation as well as an enthalpy equation, but there is a very nonlinear coupling between both the species and temperature, and it also so this is one very big problem, right, that in both in the species as well as in the temperature equations you have this reaction rate, this chemical source term, which can be either in terms of the species production rate or in terms of the heat release rate. So, but the temperature dependence is in this manner, right. This is a problem. So, the problem can be circumvented by looking for something which such that we can somehow get rid of this this chemical source term. Okay, and for that the chemical source term, what does it make? What makes this quantities non-conservative? Of course, as you see that Hs is the specific enthalpy is not a conserved scalar, neither is Yi because it has got a source and a sink term respectively, right. So, the idea is that we need to search for some quantities which is conserved during a reaction. Now, stoichiometry relates the reaction entities, and that tells us that this conserved quantities that there can be conserved quantities in a reaction. For example, this total enthalpy. Now, total enthalpy in a reaction, what happens is that, as we have seen in chemical equilibrium when we discussed about adiabatic flame temperature, is essentially the enthalpy of formation going into becoming sensible enthalpy when the reaction is complete, right. So, of course, then the total enthalpy does not change during this. So, then this suggests that if we can be intelligent, we are clever, we can find out quantities which are essentially conserved. Now, but the question is that it is very difficult to find out quantities which will be conserved in a convective diffusive medium. So, we can find out this quantities like a combination of different species mass fractions, or a combination of a species mass fraction and sensible enthalpy or total enthalpy, which will be essentially total enthalpy. But and we will see that in certain conditions we can make them conserved, but it will be very difficult to find something which is generally conserved in a convective diffusive medium. Okay. So, for now we will need to find out the coupling function formulations, and we will go into that. So, this, as I said, that the reason for the coupling function formulation arises because we have seen that both in the species equation as well as in the temperature equation, this chemical source term which is on the right hand side, that has a nonlinear dependence on both species mass fraction as well as on the temperature. Now, of course, when you have nonlinear dependence, it is difficult to solve, all right. And more importantly, that these appears in both the species and the temperature equations, which make them coupled, that you cannot solve this individually. Okay, you have to solve all of them together because these are coupled through this thing. So, when you are talking about the species equation, to once again go back to this, when you are talking about the if you remove this, when you are talking about the if you are talking about the energy equation, say, that is if you are talking about the energy equation, you have on the right hand side say this guy, this total heat release rate, and this heat release rate contains the species reaction rate, the species production rate, and the species consumption rate, and which contains of course it contains temperature, but it also contains the species mass fractions, right. And so, that is how this sensible enthalpy is essentially coupled to the species mass fraction. And when you consider the species conservation equation, of course, you see that this also contains the species production rate. Obviously, it will contain the species production rate and the species consumption rate, but this also contains temperature through the reaction rate constant. This contains in this equation temperature is coupled to the species mass fraction through the law of mass action, because omega I is described by law of mass action, whereas Yi is coupled to temperature in the species conservation equation, because omega is also dependent on the reaction rate constant, which is a function of temperature, which is an Arrhenius is dependent on temperature, right, e to the power of minus A by RT. So, this is how both this equation becomes strongly coupled, right. And of course, then it means that you have to, if you have n species like the 1000 species, you have to solve 1000 equations together, and that to nonlinear equations, which becomes very demanding. So, what we do is that we formulate this something called a coupling function formulation. So, which will not contain this right hand side at all, which will be basically, and so that we can basically solve this equation itself and gain the required understanding of how the species and temperature will evolve. Is it at all possible to do that? We will see.